So what I want to start with is describing for you. So it's a review. As I said, I'll review things today. So I'll review two things. What are quantum systems and what are classical systems? What's their main structure? So I'll start with quantum systems. Is it visible? Okay. So what you have a physical system and you want to describe it. Maybe it's okay. Okay, so you have a physical system and it's governed by some kind of a quantum dynamics. And we want to discuss that. What's the theory behind it? How do we describe it mathematically? So we start by saying this is a kind of various points which I'm going to write. You can call them postulates, but that's just a name. It's a various points which you have to keep in mind when describing a system. So first of all, where do you start? You say that state of a quantum system is described by a vector which we denote in physics like this. In a complete, well, I should say, in a suitable Hilbert space, and this vector is called ket. So this space is called the space of kets. One vector, you can just, instead of calling it vector, you can call it ket. In a suitable Hilbert space. So what's a Hilbert space? It's a complete, complex inner product vector space. I won't go into too much technicalities, but so this part is technical. What do we mean by complete? I'll just mention what it means, but we will come back to these issues, analytical issues, later on. But I should still explain what does all of this mean. By complex, we mean that the field is C. The field is complex numbers. So we have a vector space H, let's call it this Hilbert space. Let's denote it by H. H is a vector space over C, and it has a complex bilinear form. So by this complex bilinear form, is this visible down here? That you have a map takes two copies from the cross product of vector space with itself to C, denoted by this bracket. So this belongs to numbers and is defined for all phi psi in this vector space, in this Hilbert space. By this complex, we mean a couple of properties. First of all, it's not totally symmetric. If you exchange, so this is like a vector, this is like a scalar product, but a complex kind. So you have this, and then you have this form is linear. So this breaks down. But one should notice that if I put a number here, this gets complexified. This gets complex conjugated when I take it out because of this property. So it's linear in the first, but in the second, the linearity is slightly skewed. And I should mention that, like, if you look in the mathematics literature, they usually put the linearity in the first, in this argument, instead of the second. But in the physics literature, it's universally the second argument which is taken to be linear. So you should keep this in mind if you consult a book. And so this was second. And the third is the usual thing, that is positive definite. So this scalar part of any vector with itself is strictly greater than 0, except for all psi, except for the 0 vector, whose scalar product with itself is 0. So just usual inner part on the vector space, just complexified. Now, notice the following. If I pick any vector in the space, I can associate with it a member of the dual space. So consider the space of linear functions on H into the C. So this space of functions is called the dual space. And with picking any psi from H, I can construct such a member of the dual by simply writing this. So this object is a member of the dual space because I can give it any phi and this gives me a number. The action on phi is defined like this. So it's defined for all vectors. So it's I can construct just any dual vector starting from psi. So this is short-handed, written like with the flipped thing, and this is called the. It just means belongs to the dual space. And then the action of this on any vector is just short-handed like this. So when I write this, you have a bar and you have a cat, so you have a bracket, and this just means this. Both notations are used. This is shorthand, many times people use it, but it has a chance of causing some confusion. So if ever there's a confusion, come back to this. Notice that I haven't said anything about the dimensions of this vector space. So the dimension of this Hilbert space depends on the kind of system you are considering, and the dimension can even be infinite. And in fact, all real world systems, when you describe them, you need an infinite dimensional Hilbert space. Like if you consider just one point particle, nothing to it, just a particle moving around freely, no forces, nothing, no potential acting on it, has to be described by an infinite dimensional Hilbert space. So the problem becomes quite technical. However, you can consider systems which are where you focus your attention to some property of something. For example, you can consider the spin of a particle, or let's say you want to consider something which you are creating a quantum bit out of. So you are just considering two kinds of states it can have, on and off, or if a spin which can point up and down. So in those cases, mostly systems created by focusing on a part of real world thing, you can consider finite dimensional Hilbert spaces as well. So people working in quantum information usually, although I'm not sure, I'm sure they also deal with infinite dimensional spaces, but many a times their focus is on the finite dimensional spaces. But as soon as you are doing the mechanics, not like just a fictitious quantum system, mechanics of any actual particle, you have to deal with infinite dimensional Hilbert spaces. So what do we actually mean by infinite dimensional Hilbert space? Well, you basically define it by saying what it is not. So if you have if a finite basis exists, then it is finite dimensional. And as you all know, if you have a finite basis, then the number of elements n is same in all bases. And that is the dimension, so it's fixed. But if you don't have a finite basis, there's no finite number of elements which can generate the whole space, then you call it, that is a infinite dimensional. If not, infinite dimensional. So many technicalities are involved when you are dealing with infinite dimensional cases. We won't deal with them right away, but for now we will give a working picture of such a space and worry about exact details later. So this is how usually the physicists work. They just don't go into defining things very carefully, just make a working model and go with it as far as it can take you, but finally some technicality hits you and you have to come back and correct. This kind of attitude towards working with mathematical objects is different from what mathematicians usually do. It has its pitfalls because you can run into problems, but that's the whole idea, that you want to make as much progress as you can and you discover the pitfalls by encountering them. You don't want to restrict yourself immediately by defining things extremely carefully. So I'll give you a working picture of infinite dimensional space, and it's essentially how Dirac thought of it. And then von Neumann, he came back and he fixed things up and defined things more carefully. So, but I should say something about this thing. I've mentioned everything, but I haven't mentioned what is completeness. So this is just in the sense of analysis, that you consider, you want it to be complete in the sense that all Cauchy sequences converge and have a limit in H. So if I remind you what's a Cauchy sequence, you don't need to worry about this part right now too much. So if you have a sequence, and then I can, so this convergence is in the sense of you define a norm topology on it. Norm I can define very easily just by the scalar product, the inner product I have defined. So the norm would just be this. And in this norm, a sequence is Cauchy if for every epsilon greater than 0, there is a number n, so that when you go far away in the sequence, you are essentially bringing them together and together and together. It's a sequence which kind of zooms in, and for all mn which are greater than this n. This is fine, but the point is that you want to have it converge to an actual element of the space. This is, you should think of it just like completeness in the real number system. If you focus just on the rationals and make Cauchy sequences, they are not guaranteed to converge. They don't converge. So you have to expand it to include the reals to converge. So you don't want to have that kind of a problem. You don't want to have it incomplete in that sense. And you want it to, all these sequences to converge to an element. Because if you don't have this, you can't make progress towards more rigorous treatment. But this issue of completeness is only an issue when you are considering infinite dimensional spaces. All finite dimensional Hilbert spaces are already complete. There's no issue over there. So in this norm, I should have a scale traditionally. So let me come to the working picture. So working picture is due to a theorem. So I have this theorem that all finite dimensional Hilbert spaces are isomorphic to Cn. Essentially, you have a list of complex numbers, and usually instead of a row, you like to think of it a list in a column. So just like I'm sure you are aware of it. This result from the linear algebra that everything can be just mapped to these columns, and every time you have a vector, you can literally think of it as a column and deal with it. But what happens in the infinite dimensional case? Well, in the infinite dimensional case, there is another technical requirement. Maybe I should have just said that the Hilbert space, because all the Hilbert spaces we deal with have this property, because I don't know what to do if it's not there. So separable Hilbert spaces means that they have a, by definition, this means, although you don't need to worry about the definition, is the definition, what is important is what the definition then implies. But the definition, if you look up in the book, it says that it has a countable dense subset. So dense, that means that if you consider any open set in the space, it intersects with some element, at least one element of this dense set. Of the set, then the set is dense. So again, the picture, always you can remind yourself of the real line and the picture becomes clear. So the rationals are countable in the real, but they are dense. You can make a open set which does not have a rational in it. So in this sense, they kind of are spread everywhere and they touch everything in that sense. So we want our Hilbert space to have that kind of a property. It should have a countable dense subset so that we can deal with it. So for example, suppose you are dealing with real line. Obviously you can write theorems, but if you ever have to write anything on your computer, ever compute anything, you need a rational number. You can only write down a rational number, except as a symbol. But the good thing is that the rational number approximates the whole real line because of this dense property. So in this, again, this sense, you have some kind of a countable dense property present in this. And as a result of this property, you have this V's theorem, which is a counterpart of that theorem. It says that every infinite dimensional separable Hilbert space has an infinite basis in the sense that we have a sequence of vectors. So you have the sequence. So that every vector in H can be written as this. Where alpha I is a unique sequence. And furthermore, these I, this is a countable set. It's a sequence, so it's a countable set. So alpha A is a unique sequence. So you have these kind of bases. They are infinite sequences, but you are assured that if you pick any vector, you can write it as a linear combination, but an infinite sum, but these numbers are unique. So it kind of gives you can literally make a picture that it's those kind of columns, but they keep going. So as a starting point, you don't have to worry too much about what is this infinite dimensional thing. You can think of that you're dealing with infinitely long columns, essentially sequences of the numbers. And then there's a theorem, another theorem, which is essentially this. So like if I have picked a basis, I can express it using these numbers. And that's what the theorem says. It says that every separable infinite dimensional space, I should really write infinite dimensions, is isomorphic to L2 space. What's the L2 space? L2 space is just this space of columns, but with nice norm properties. This sequence of complex numbers whose sum converges. You take mod square and you add all of them. This is a convergent series. So every separable Hilbert space essentially can be mapped to these kind of columns which have a finite norm. Although we can map everything here, but other realizations of H are still important. For example, you can consider this space L2 AB. This is, you have functions here which are integrable over this interval AB with this added property that this is always finite. And so they are these integrable, you can just say it's this. The mod square is finite. And you can even take these A and B, you can consider this space for this. So that you're putting this condition that over the real line, this is finite. So these are called the square integrables. And you can, because you want to define, you have functions at your hand, So you want to define some operators. Finally, we're gonna come to operators acting on these. And when you have functions, the easiest operators to consider are differential operators. So you can tighten this condition. Instead of having integrable, you can say, well, C1, C2, C3, sometimes you consider C infinity. I think up to all C infinity, they all form Hilbert spaces, infinite dimensional Hilbert spaces. So these are also an example of Hilbert space, although they all can be mapped here, because essentially you can do this to them. But this is still important because once you have these functions at hand, why this is important? Because we can have realization of different operators. So for example, we will see in a minute that physical quantities, they have some operators associated with them. The reality of those operators, we will see in later, is in the algebra. But given an operator, you may not be directly able to see how to implement here. So an operator here in this realization would be something like an infinite dimensional matrix. But you may not know how to construct that infinite dimensional matrix. And it may be possible that to realize that algebra over here using differential operators may be much easier. So you're not discarding these, but this is always available. So one strategy for now would be to focus on finite dimensional Hilbert spaces, take their obvious properties, which are just essentially complex linear algebra, and just assume that it also holds in infinite dimensional case. This is not true. It fails at many cases in many instances, but this could be your starting step. And you then later on check what I'm doing, is it sensible or not. So this was just the first point, that how to describe a system. A system is not any coordinates, any particle, anything like that. It's just a vector in a Hilbert space. So was it that board, this board? Let's go to the next point. Is there any question?
Sir, any physical finite dimension space? Any physical मतलब कोई example है सर इसकी, जैसे आपने अभी बताई, but finite dimension की आपने spin से आपने बोला, तो infinite.
I said कि अगर आप simplest भी कोई system ले लेना, for example एक particle moving around, you find out that you have to describe it using a vector in an infinite dimensional Hilbert space.
Not the position like x, y, z.
No, not x, y, z. It has to be a vector in an infinite dimensional Hilbert space. So this question was very important because it tells me, I was worried maybe people know this stuff. It shows that people are not aware. So it's a good thing that we are reviewing. And it also tells me maybe I have to give some kind of a homework where you do these simple practices to get, because I can't like totally review. I thought about doing one system, but I'm thinking of doing a not free particle, some other system, which is a bit more complicated, but it will teach us how to quantize a quantum field. So I will do one system, one quantization. It's a particle attached to a string. Very close to a free particle, but this will tell you that you just cannot even deal with one particle using finite dimensional Hilbert spaces.
What if these Zi is represented in case of infinite dimensional spaces? Because in case of finite dimensional spaces, we know that how the bases are working out and everything. So, but over here, what is they represent?
Well, they are again basis elements, and it could.
Let's say if they represent a particle moving around, right?
No, they are like.
Let's just if we pick this example, then in that case, what would these ZIs would represent?
Well, again, there are like infinite number of subspaces. You can give interpretation to all of them.
Okay.
Many a times, what happens is that these bases come from some sort of eigenvectors of a operator. So then they represent these eigenstates. So then these could be, for example, the eigenvalues for that operator.
What about the physical interpretation?
Right.
We don't know that.
No, I mean if they're coming from as eigenvectors of a operator which is related to some physical observable, then these are eigenstates. Eigenstates have a very specific physical meaning. I'm coming to that. What does this mean? So this was all. How do you encode a state? By the way, I should say one word about state. A state means that this is all you have there to know about. It's not like you have partial information. Everything there is to know is all contained in there. There's nothing more, nothing less in the theory. So, but once you have the state, what information is there? How to take that out? What does it tell you? For that, you have other procedures. So first of all, you have observables. These are just things which you can measure. Like if you have a free particle, you can measure its speed, its position. If it's like a merry-go-round, you can measure its angular momentum, angular speed, things like those. If you have a quantum bit, you can measure if it's on or off. So any procedure where you measure and you get an answer, that's an observable. Now, how to describe these observables? But to go towards there, I have to discuss something else. You have linear operators. So you consider a linear operator A on X. For finite dimensional case, this is always true that given a linear operator, there exists another linear operator A dagger such that if I take any two vectors, apply this operator on this and take the scalar product, there exists such a operator that these two answers are same for all psi and phi. This is called the adjoint.
Inner product में तो सिर्फ preserve करता है.
No, inner product preserve की language यहाँ use नहीं होती. ये इधर act कर रहा है, ये उधर कर रहा है. बस आपने इसकी placement change कर दी. So when this happens, well, this will always happen. If it's the same operator, then you call self-adjoint. In physics, some people call it Hermitian as well. Now, in infinite dimensions, this is generally not true. If you take an operator which is linear, no such operator will exist, which is adjoint of it. At least not for all vectors. The main problem is in infinite dimensions, domains are an issue. So you have a linear operator defined on all of these. You may have an A dagger which works on some of those, but not all. And the domain may be different. The domain of A and domain of A dagger may be different. However, there are certain kinds of operators, bounded operators. They have adjoints. What's a bounded operator? I don't really need to. I can define it as a one-line definition, but it won't tell you much. Essentially, some operator which doesn't take you very far away where you start from. But to define it, you need to put a topology on the operators. We will do it later on. And in that topology, it's bounded. Well, maybe I can just write it down. So operator is bounded if there is a K. So you have a kind of a upper limit on where it can take you. You start with a norm of the vector. When you apply with A, the norm doesn't just keep going. Norm is bounded by some K. So for these operators, they all have adjoints. But unfortunately, the operators which we encounter in quantum mechanics, almost all of them, they're unbounded. So we have no guarantee of adjoints existing.
So reason इनकम्पोजिट है कि आइगन वैल्यूज हैं फाइनाइट
नहीं.
Sir?
Wait a second. We encounter unbounded. So what you have is domain of A in general. These domains, they do not match. And in fact, there's a theorem that if you have any operator which is defined on the whole space and has adjoints, then it is self-adjoint, then it is a bounded operator. What's a self-adjoint operator? Written over here. So if it's defined on the whole space and is self-adjoint, then it has to be bounded. So most of the operators which you encounter in quantum mechanics, they cannot be self-adjoint, but they can be what we call essentially self-adjoint or may have self-adjoint extensions. We can't go into this theory, at least not at this point. But the main idea is that when you don't have this self-adjointness available, you define a symmetric operator. And your actual operators, which you deal in quantum mechanics, are usually densely defined symmetric operators. So that means they may not work on the whole Hilbert space, but they work on a dense subset. So they are kind of good enough. And what you have is on the domain of A, this is true. This equation is true. I'm not defining an adjoint, I'm just directly defining sort of a self-adjoint, but which is just symmetric. This is symmetric, definition of symmetric. And if domain of A is same as domain of A dagger, then the symmetric operator becomes self-adjoint. These essentially self-adjoint operators, which are very close, they're densely defined, symmetric, they are as good as the self-adjoint operators, but what are the technical challenges which are there, we will probably discuss it later on in the course. For now, I could have probably skipped all of it and just told you that these self-adjoint operators exist, because what we want to deal with is these self-adjoint operators. They have one very important property, which is at the heart of how to connect observables with something like self-adjoint operators. One should also keep this picture in mind. Because of this isomorphism of any Hilbert space to L2, either Cn or L2, we can think of these operators as these matrices. So Aij is the matrix element. In the finite dimensional case, it's just simply a matrix. And in the infinite dimensional case, you have an infinite dimensional matrix. Well, an infinite dimensional matrix is not just saying it that it's infinite dimensional doesn't mean much, except that it gives you a mental picture. Otherwise, you have to deal with it using more analytical tools. The thing is that if you have this, this would be this, just like usual. The matrix elements of the adjoint would be transposed and complex conjugated. And you can go from here to here using a basis. So if you have a basis, these are the matrix elements of this. How do you read it? You apply A on I, and from the bracket notation, you're taking a scalar part of J with I. And these I belong to the basis, I and J. Now, the good thing about these self-adjoint operators is that their eigenvalues are real. You're dealing with a complex space, so the eigenvalues of general operators could be complex. And also, I think as Ramla asked, like what it has to do with anything physical. So this is where the physics comes in. You have to pick some numbers to describe what you observe when you measure. So those numbers are related to the eigenvalues. And since everything you measure is a real number, So you want your eigenvalues, you want some reality to come in, and what happens is you say that eigenvalues of self-adjoint operators are real, and in an experiment or in an observation of an observable, so I'll use the same symbol for the observable and the operator associated with it. So suppose observable is A, let's say angular momentum. This operator is usually written as A hat. In an observation of an observable A, one of the eigenvalues of the associated operator comes out in your apparatus as a long curve. So today's lecture is essentially about mostly pitfalls and not totally resolving them. This statement which I have written is also not correct. Why? Because the thing is, many interesting observables, their corresponding operators, they don't have any eigenvectors. They don't have eigenvalues. But what they have is what we call a spectrum. Spectrum is a sort of a generalization of eigenvalues. So what's a spectrum? So consider for any operator A, define the resolvent like this. So the kind of thing which you used to write to compute your eigenvalues in linear algebra. So set of lambdas for which this does not exist as operator on all of it they form lambda belongs to complex. I is the identity operator. They form the spectrum. Now in finite dimensions, spectrum is a countable set. Yeah, so for finite dimensions, it's easy. Everything is easy in finite dimension. That's why I said always keep in mind finite dimensions and only worry about infinite dimensions later on. So it's a countable set, you have a discrete spectrum. While for infinite dimensions, spectrum can be countable and discrete and can have both parts. In infinite case, spectrum has both discrete and continuous intervals. Now there is this theorem which says that it's the general theorem, finite or infinite dimension doesn't matter. Eigenvalues may not exist, but the spectrum of self-adjoint operator is real. So you want to associate somehow the spectrum values with what appears in your measurements. So theorem spectrum of a self-adjoint operator is real. Now, for this case, it's easy. If you measure what I wrote, you will get one of the eigenvalues. So in this case, if you measure, you will get something out of the spectrum, some number out of the spectrum. But since it has a discrete part, so you will be making some small intervals, because your actual apparatus is not going to give you a real number. It's going to give you some within some error, some interval. For discrete part, if you find a spectrum of an operator, it may have discrete and continuous part. For discrete part, the eigenvectors exist. So I can write them like this. Lambda is the eigenvalue. So I label the eigenvector with this, but I have an extra label because you may have more than one linearly independent eigenvectors with same eigenvalue. If you just take an eigenvector and just scale it with a complex number, it's still an eigenvector. Forms a one-dimensional space. But that's not it. You may have a bigger space which has more than one linearly independent vectors. So you have a bigger dimensional space, all having same eigenvalue. So then you can pick a basis, and so this is what I'm showing over here. But for continuous part, unfortunately, no eigenvectors exist. However, for convenience, I mean, this is what Dirac did. You still formally define some generalized eigenvectors. We formally define some eigenvectors. So you have a discrete part. This is coming from, sorry, a continuous part from continuous spectrum. You still write something like that. What you find, what you can show, that no such vector exists in the Hilbert space. But this didn't stop Dirac. He said, okay, if they don't exist in the Hilbert space, let's just throw them in. They will not gel well with the other vectors of the Hilbert space, but you can write formal expressions so that they become very useful.
So if we have self-adjoint operator finite dimensional, then we say the spectrum and set of eigenvalues are the same.
Yeah, exactly. So let me give you, because this is an important point. And this is probably the point where, like in practice, in finite dimensional, even for very, very simple calculations, like if you're doing first year quantum mechanics, you don't know much mathematical theory, you still have to deal with this thing. And this is where it differs from what people in quantum information do. It differs from that. So how do you do this? What did Dirac do? So for example, I'll give you some examples of this. consider this space L2, like which we defined of square integrable functions, and define the operator so these are square integrable functions. Define the operator, this thing, x hat, it acts on a function and gives you this function. F multiplied with x. This is called the position operator. This is symmetric, essentially self-adjoint. You find that the spectrum is the whole real line. But no eigenvectors exist. So Dirac said, let's consider these vectors. This is Dirac's delta function. It's not a function, it's what people call a distribution. In the sense, this is defined, I'm not sure how many of you have seen it. And actually, if you integrate it, so one should think of it as a very sharp peak. Sharp peak with unit area at the point x dash. So if I integrate this function, it gets chopped here. And if I integrate it within some limits, where x dash is not within this interval, then I get a 0. It's 0 everywhere except at x dash. It's called Dirac's delta function. It's not a function. It's a very ill-behaved kind of an object. So it's not part of Hilbert space at all. It has no norm, no nothing. It's certainly not square integrable. So it's not part of Hilbert space, but you still define it and do some formal operations with it, and it becomes very useful. I'll come to it in a minute, that what we can do. Similarly, you can define this operator on this space. Well, for this, you need at least, instead of L2, you consider C1, which have C2, which you can differentiate. Take this operator. This is called the momentum operator. With suitable choice of domain. So that's the difference between bounded and unbounded operators. Bounded operators, they're self-adjoint on the whole Hilbert space. For the unbounded operators, you can't make them self-adjoint on the whole Hilbert space. You have to restrict space. You have to pick that on these parts, and it has to be, you want it to be densely defined so that you can do whatever you want. It becomes self-adjoint on that restricted domain. So with suitable choice of domain, this is self-adjoint. And spectrum is again real line. But again, it has no eigenvectors. As I said, that this is a general phenomenon. You will never find eigenvectors. Actually, there's a theorem. All of these kind of operators which have continuous spectrum, they can be unitarily mapped they are unitarily equivalent to the position operator. But we don't need it right now. So it has no eigenvectors. But then you say, okay, I'm gonna construct some. Let's take this. If I take this, then this action is just this. And it does have this eigenvalue. It's an eigenvector, but it's not in Hilbert space. You just say, so you say, okay, I'm just going to throw it in. I'm just going to work with it. Although strict mathematicians, they wouldn't do it. They would use other methods and define very strange objects, define what they call operator value distributions and work with those, but this is pretty good enough for a lot of purposes. So you just have to be careful that since they are not in the Hilbert space, they may cause trouble sometimes. So you have to be careful with what you are doing. Being that careful is essentially what the Fourier theory is, because when you consider Fourier transforms, this is what you're dealing with. So it's essentially the same. We will come to it in a minute. What time is it? When did we start?
5:30.
I thought I will be done with these. I'm only done with 6 pages. 22. Okay. Let me stop after some time. I'm not tired. I don't know what you guys. Okay, there are further theorems which we need. So if you haven't studied quantum mechanics, just keep in mind these theorems. This is just essentially some complex linear algebra. I think it shouldn't be difficult to absorb it. So one is that eigenvectors. Okay. Eigenvectors belonging to distinct eigenvalues are orthogonal. So if I have an eigenvector, another one, there will be 0. Lambda is not equal to lambda dash. So this is, remember, when I write this is just the scalar product. So 0 if the eigenvalues don't match. And one theorem, another one, eigenvectors belonging to same eigenvalue span a subspace, so that one can choose an orthonormal basis. So all of this, that they are real, they are orthogonal, they are subspaces if the eigenvalue is same, leads to resolution of identity. This is the most basic object to do various manipulations. So the identity operator can be written like this. Lambda is the sum over all the eigenvalues. But if the eigenvalues, they are not all correspond to one-dimensional subspaces, then if, for example, if you have one eigenvalue which is belonging to a three-dimensional subspace, so then you pick a basis. So then this is the sum over that basis elements. How you pick doesn't matter.
Sometimes it is called completeness property, right?
Yeah, this is also called completeness.
Why? Completeness inclusion.
Or this completeness is in the sense that you can write any vector. This basically allows you to expand a vector in this basis. So if I apply it on a vector psi, I get psi back because it's identity. But now it's written, these are some numbers, and it's written as a linear combination of these numbers. So you can write these as like this. So I just applied the identity and I got the expansion of psi in this basis. Now, this would be true if I'm in finite dimensions. No, not necessarily finite dimensions. Even in infinite dimensions, some operators can have completely discrete spectrum. So actually, there's a theorem that if you have what are so-called compact operators, they have a completely discrete spectrum. But most of the operators are not compact, not even bounded. So they have both parts. So if you have both parts, so in general, this completeness looks like this. On the discrete part, you just write the same thing. Then you have this. Again, this is not rigorous. There is a rigorous formulation of it in what they call projected value measures. Maybe we will discuss it someday if we need it. I don't know. I don't want to make it a course on formal quantum mechanics only. But it's not rigorous. This is this kind of operation. So these fictitious eigenvectors which you have put in, their labels are continuous because these labels come from the continuous spectrum. So you write something like this. And then this becomes a formal expression. I'll show you the uses of this formal expression. Formal in the sense that these objects do not really exist in the Hilbert space, but they are still very useful. So just for a little practice with these kind of guys. Red use like or blue? Blue मैंने use किया नहीं?
Green.
क्या?
Green.
अच्छा green नहीं किया.
Yeah.
So some practice. If I take these formal vectors and write these things. So for example, this is supposed to be scalar product. And I use the formula for the scalar product in the L2 space. The formula in the L2 space of the scalar product is this. If you have F and G, this is the formula. So I just do that, and these were supposed to be the Dirac delta function, which are supposed to be real. So I get and I just do the formal manipulations. So my formula tells me when I do this integral, this x is replaced by this argument. So the integral is gone, and I'm left with this. By the way, this is symmetric. Doesn't matter which one you write first. So what is this? This is saying that this is non-zero only if that's the property of the delta function, when x double dash is equal to x dash. So this is saying 0. So this is telling you orthogonality.
So black would better.
Okay, orthogonality of the eigenvectors. So formally you have what you wanted, because that's why you created these eigenvectors. Really, black is better.
Yes.
At least I can see do better. Reflection.
I'm not sure what it is, but
Okay,
it's good to see right now.
everyone agrees. Okay. Check this. If I compute the matrix elements of the position operator, this is how position operator x on these functions, on any function, just multiplication with x. So this gets done. And what is this? This is just saying that matrix elements are diagonal. Formally, because it's not like a discrete thing, but it looks like this is something diagonal. If x dash is not equal to x double dash, here you get a 0. And I can check the resolution of identity. So this is the identity, like I written over there. So if I apply it on psi, on any ket psi, in this space, this formula should look like this. This is this vector. And then I have to compute this. I have to see what is this object. This is already a scalar product. So if I compute this, this is this. So this is psi of x dash. So remember, when you do this, psi projected onto x dash. These are scalar products, so these are projections. So it's giving you like the component of psi along x dash. So what's it saying? That these functions, they have components along x dash, which are just the values of the function at that point. So if I consider this thing, this is the function. These are the projections along these vectors. So, but I put this in. So this thing becomes and this is just psi of x. So it really was identity. I got psi of x back. Now the other operator, which also didn't have eigenvectors, their operations look slightly different, although it's all dual to it. But those you will recognize more easily. So this momentum operator, if I take its eigenvectors and compute check their orthogonality, because I need the orthogonality to define this completion. This is just the scalar product of this guy and the complex conjugate of this guy. This guy. This is a representation of the delta function. So that means that this is 0 if k is not equal to k dash, and this is thus the orthogonality. You can check this kind of expression as well. That's very easy. Let's check the identity. That's slightly more interesting. So this is supposed to be identity. When I apply it on a vector psi, I get this. Pk Ei kx, and then I have a scalar product psi and k, which is this. But can anyone tell me what is this? What's this object? This is the Fourier transform of psi. Psi of k tilde Fourier transform. Of psi. And then what is this? This is the inverse Fourier transform. So this gives me the psi back. So it really is identity, because this is inverse Fourier. So actually you can think of that this theory that is all legitimate to use these functions is equivalent to this actually the theory of Fourier transforms. Now I write the next prescription, next postulate. Unfortunately, I can only use one color. I was planning to write postulates in some different color.
सर रेड सेंटर वाले में लिख के देखो, सेंटर वाले ज्यादा अच्छा।
पहले तो ये नहीं आता। रेड में ट्राई भी नहीं किया।
नहीं किया।
So when we make measurement of this is very smooth. A hat, which is self-adjoint. Whenever I say observable, there has to be self-adjoint operator. The probability. So this is the physical connection of getting the outcome lambda is this, and I can put an equality over here if I assume that psi is normalized, which is always possible. Just scale it and normalize. You have a sum over here because you don't know where it's going to fall along which direction in the, so you got the eigenvalue lambda if it's corresponding to some eigenspace, so it can come from many different bases of these, so you have to sum over these. So for one-dimensional subspace for lambda, this would be much simpler. This would be just this. Similarly, if the outcome lies in this continuous part of the spectrum, then you have probability density. Then obviously you have to define not absolute probabilities, the densities, and it's the same thing. Notice this thing over here. This is coming from here. This p lambda or this p lambda, small p lambda, which is the density, are unaffected if I replace the psi. So remember what's happening. I am in a state psi. My system, I said it will be described. I'll tell you what is state by telling you which is the vector. So it's in some state psi. And I make an observation of an observable, which is A. And I want to find that what will be the outcome. The first thing quantum mechanics tells me that it will be one of the eigenvalues or one of the numbers from the spectrum. Which one? Take the state, take the scalar product with the corresponding eigenvector. And that square will tell you the probability. But then I notice that if I change the state by this, the probabilities are not affected or unaffected with this. Because this phase gets cancelled in this mod square. So what you then have is that a system is described by a state up to a phase. Doesn't matter which phase you pick, you can always say in the phase, it doesn't matter. So that's why sometimes people say that system is described by a way. The overall norm you have already fixed. You said, okay, I'm going to make it 1. But even if you make the norm 1, multiplying with phase doesn't change the norm. And the phase doesn't matter. The next thing, so I'm sure at this point, people over the Zoom, many of them are quite well versed in quantum mechanics. They have started getting bored. But it's just the first lecture, we will be done with it. So the next thing is, next point, kind of a postulate, is that after the measurement, that has an outcome lambda. The state suddenly changes. To another vector, which just belongs to the subspace to the corresponding subspace. And if the subspace is one-dimensional, you can just write it as lambda. Because overall, you're going to make it normalized, doesn't matter. Phase doesn't matter. So it's just, you're just picking one vector from that one-dimensional subspace. You can label it with lambda. But otherwise, you have another label. Maybe I could have called it lambda alpha. Yeah, that's better. So it suddenly changes when you measure. You get an answer. You could have got lambda. You could have got lambda tilde, lambda dash, whichever you get, you collapse to corresponding subspace. So what does all of this mean? All of this means that if we know that system is in state psi, we are still not sure that what would be the outcome of measurement of an observable A. There's a distribution of values of the spectrum. Anything can come up. There's a probability distribution over there, that which one has what probability depending on in which state you are. That probability distribution depends on the state in which your system is. And you can then, to quantify that probability distribution, you can use the usual kind of measures which you use to describe probability distribution. For example, for this observable, it doesn't have a set outcome, it has a distribution. So you can talk about its mean, and you can compute that the mean in this state psi would be just this. It's not a postulate, it's coming from the probability postulate. It's coming from here. Similarly, you can talk about the variance of A in state psi, and that would be just the statistical formula. I'm not doing anything. It's just you compute it using this formula. However, so everything is probabilistic. But notice that if you are in an eigenstate, then you are sure that only this will come up. Then this probability, what happens to this probability? If let's say if I am in state lambda dash, then this is the probability. And this probability is 0 unless lambda is equal to lambda dash. Then I have no forms that what will come up. Then I'm pretty sure, exactly sure that what will come up. My probability distribution is all peaked at lambda dash. So then your mean is just that, and then your variance goes to 0 in that case. But in general, you have a variance and all the other moments of the probability. This is a very important theorem. It's kind of at the heart of, well, there are many things at the heart, but this thing tells you something which is kind of very famous about quantum mechanics, which changes it, which differentiates it from a usual kind of statistical theory. Like in general, even in classical thing, people were doing statistical mechanics, and people knew that if I'm not sure about things, I can do a Pauli distribution. But you have over here this kind of a thing. For two commuting, it's actually when this thing does not hold, that's the more interesting part. For two commuting operators, we can find a common set of eigenvectors. And this is not usually possible. I should say most often it's not possible. For non-commuting operators. So if they have common eigenvectors, that means if I have my system in the common eigenvector, then I'm sure about both of those. There's no uncertainty. I can prepare my system, I can bring it to that state so that I know both of them, so that there's no uncertainty in either of them. But this is not possible for non-commuting operators. If you make the system such that you know one exactly, you wouldn't know what's happening to the other. Actually, you can quantify this by computing the variance, and there's a inequality which you can derive. So it's the commutator which captures the non-commutativity. You can take the commutator. You want to know that if I'm in state psi, what's the variance in A and what's the variance in B? You take the product of those. It would be this. And since in general, if the two operators are non-commuting, then this number will always be non-zero. So that means you cannot bring both invariances to zero. If you reduce this, this has to go because the product has to be more than this. If you reduce that, this has to go. One thing I forgot to say right at the start of the lecture is that in whatever I'm doing, I'm putting h bar, which is a parameter in quantum mechanics, equal to 1. I don't want to carry it around. No one does. But if you have to compare with actual numbers, then h bar is there. So this effect is very small because h bar is small. I mean, it's not small, it depends what you are comparing with, but compared to our everyday numbers, quantities, this is small. That's why we didn't discover it before, but if you are going to atomic levels, this is very pronounced. So should I finish the quantum part and then take a break, or what? Should I go on? I'm fine. I'm asking you. Are you guys fine?
How much is left? Is commutator पे कोई restriction है?
एक second. How much is left? I think half an hour, less than that. I'll try going fast. Ji.
Sir, is commutator के ऊपर कोई restriction?
These commutators will be different for all kinds of operators. Depend करता है कि क्या है. So, for example, if I take this as the name suggests, जो मैंने operator discuss किए थे, X and P, they actually are related to actual positions and actual momenta. So if I do this variance in position and momenta, this commutator for those guys is actually just a number, iota h bar. So I in this mod goes away and psi is normalized. So that gives you a 1 So this is just h bar by 2. In general, it won't be a number, it will depend on state. But in case of position and momenta, it has to be more than this. It's not saying that it will be exactly this, but minimum you can bring it to this, not less than this, but it could be even larger. Here I'm just at the end of it, pretty much. The only thing left, I have basically given you the description of quantum mechanics, is the time evolution. How the system, you said that the system is in state psi, but in classical world, systems do not stay where they are. Right now it's at this state, if I leave it, it's gonna change the state. So how are the things changing if you start them in some state psi in quantum mechanics? By the way, whatever I'm saying is true for any quantum system. It could be a particle, it could be a field or whatever. This is all just general theory. So the last point is, and then we have kind of given you the description. Not done any example, but at least the description is there. Time evolution is unitary. This is absolutely essential for conservation of probability, since probabilities do not make sense if they don't add up to 1. So needed for conservation of probability. That means if the evolution is not unitary, the probabilities will, after some time, no longer add up to 1, which makes no sense at all. There's no interpretation of probability where it doesn't add up to 1. So a quantum evolution which is not unitary does not make sense for a closed system, unless you have an explanation like probability is leaking, some part of the system is going out. For a closed system, it just does not make sense. So quantum mechanics evolution has to be unitary. You have no other choice. What does it mean that it's unitary? If this is your state, now I'm putting a label, a time label, just to indicate at what time the state system was. So as the time goes from t naught to t, I expect to have a new state. This state, for probability conservation, I won't go into too many calculations. Just write this. Will be gotten through action of an operator, which is unitary. Unitary in what sense? Unitary means that this scalar product I could even have another vector here. This is same as for all phi psi. So this essentially means if I bring it here, then this would be the joint of it. And by the way, for the unitary operators, you have to again worry about all those technical conditions, but let's stop talking about them for now. Because in finite dimensional, they don't matter. In infinite dimensional, they are kind of way too hard. So in the starting point, it's better to just think as if you're doing finite dimensional. So this comes here, but then this has to be equal to that. So this you need to be 1. And also this to be 1. So in other words, if I make the matrix of it, the Hermitian conjugate is equal to the inverse. Now, from this, For nearby time, if I do it for nearby time, I can for nearby time t and t naught, I expect that this operator should be close to identity, in the sense that when I take the limit, t goes to t naught, nothing should happen. It's a continuous change, it's not a jump. So I write it like this. It's just some parameterization. I put it in here because when t goes to t naught, this goes away. I get an identity. I is just by convention minus I. So I need an operator because the whole thing is an operator. This is some operator. Now I want this thing to be unitary. For this to be unitary, one is already Hermitian. When I do the dagger, iota changes sign, and I get dagger. So if I do this u dagger u, I get 1 and minus so to this order, for this to be equal to 1, this was dagger. What do I need? I need for these to cancel. I dropped the second order term because I'm assuming this t minus t naught to be very small. So to the smallest order, for this to be unitary, I need this to cancel with this. So that means h is h dagger. So this operator, which I have written here, which depends on this time t naught, is Hermitian or self-adjoint. Now, in the case, for special cases, which are actually very, very common, where this does not depend on t naught. So no matter which time you start from, the operator which comes over here is same if you just want to move a little bit ahead. So this is called this one, generator of time translation. This is the time translation operator. This is the generator, which is Hermitian. It is given another name, Hamiltonian. So if the Hamiltonian is always same, no matter which time you start from, then you call it a time independent evolution. Or you say that it's a time independent Hamiltonian. In that case, you can do something very neat. A finite, this was very small. A finite evolution now t and t naught are not close, but I can build it up by small steps. Take a large number of these steps. For this formula to hold, you have to take them infinite to make up a finite jump, finite thing. And each step is very small. Now this delta t is obviously just this t minus t naught over n. This is the step size. Delta t minus t naught over n 8 to the n. So this is a kind of a product of operators, and I'm taking a limit. So this you can write, you can define it this way. You call it, because this is that looks just like an exponential. You call it this. And actually, it's really an exponential in the sense that if I write the series of this exponential, the Taylor series, for example, then I can show that these two are same. The product of these operators is equal to that series, which is essentially I've done over here, because this exponential is defined as a series. So it's a series of products of operators. Very unambiguous because it's only powers of one operator. So there's no like difficulties in making the products. So the unitary operator, not a small one, a regular one, can be written using an exponential and a Hermitian operator called Hamiltonian, using this kind of exponentiation. And H is called then the generator. Now, here we build up a large number of steps and got this expression. We can go in the other direction, which is take the limit of this equation. So if I write this, psi of t plus delta t is u of delta t. Let's say I'm starting from time 0, so that I don't have from time t. This for small delta t is this. That's what my assumption was. My ansatz was. So I bring it here. And divide by delta t, take the limit. And here is limit free. So this is some parameter. This is my Hilbert space. I'm mapping a parameter, a line, into the Hilbert space. As I go along, as I change t, I'm continuously going around in the Hilbert space. And that evolution is described by this. So this limit gives me that derivative. I can bring it here. So it's just a consequence of saying that your evolution is unitary, that you have Schrödinger equation. So the infinitesimal form of unitarity. Now truly the last part. Yeah, truly the last part. I have only 1.5 pages. So one should note the following. Note, physical quantities. Physical measurements are probabilities or physical predictions. That's the physical content. I don't care how the state changes. I cared about it because that tells me how the probabilities change. So if I take the probability of an observable A to be, give me an eigenvalue, let's say I, that I had already had an expression for it. But then I wait and I ask, what happens to this probability after some time t? So I am now tagged in a label t, which tells me how this probability changes with time. That's the main physical content of the theory. So that would obviously be just what I had already written my postulate. It's just this, that what the state is at that time. But that I can write as this, what the state was at time 0. For any operator and any eigenvalue I. So this tells me how the probability change. But then I think of it, this is not acting here, this is acting here. Remember, when it acts here, it's an operator. When it acts on the other side, is the adjoint of that. क्योंकि अगर मैं इसको उस notation में लिखूं, comma डाल के, so when it goes to the other side, it becomes the adjoint. So people don't bother doing that. When it's acting over there, you can write an arrow, and you can say this. So you could say, well, if, what the hell, let me just write. This is same as this. So then you say, well, I could say that the state did not even change. With time, the state doesn't change. It's the eigenvectors which change with time. Because it has the same predictions as if you imagine that the state is changing. But how could the eigenvectors change? Eigenvectors of an operator with a particular eigenvalue, they couldn't just change. How could they be changing? So if it changes, if I changes to something like I of t, how come it is still eigenvector of the operator A? Well, the answer is it is not. So what you say that the operators themselves change. Operators change with time so that new operators at time t have this it as eigenvector with eigenvalue, with the same eigenvalue, because our question is about the same eigenvalue, with eigenvalue I. So what could those operators be? Well, it's very easy to write. So if I say that A does not just remain static, it changes with time, and I say that it changes like this. This conjugation, then I can check that with this A of t, when I act it on I of t, I have this. So these cancel, and I have the eigenvector at time 0 of A. This gives me the eigenvalue I, which comes out. This is just I of t. So I find that if I let the operator evolve like this with time, then the eigenvectors have to evolve as I wanted. So you have then this alternate prescription of how the changes should be incorporated in the quantum mechanics. You say that the states do not change, it's the operators which change. You have two options: either operators remain same and the state change, or the state remains same and the operators change. Option 2, states do not change, operators do. This is called the Heisenberg picture. The original one was the Schrödinger picture. And this is how they change. Now, if I do the same analysis which I did, like writing the operator like this for a small amount of time, and I again take the limit. तो बस क्या करना है मैंने इनको मल्टीप्लाई कर दिया, डेल्टा टी स्क्वायर की टर्म्स को ड्रॉप कर दिया और a of t को इधर लाके लिमिट ले ली डेल्टा t से डिवाइड करके. So I'll find this. It's just one step which I'm leaving. Maybe I can just write. You can see that this is going to give you this commutator HA minus AA. And when I take the limit, I get this. There's an I here. This is called the Heisenberg equations of motion. So I'm done with this part, and if you come back at 8, then I can tell you how the classical mechanics works, and then we will be all set to move towards the actual work.
Heisenberg or Schrödinger equation different it's an equivalent.
Huh?
The Heisenberg picture and Schrödinger picture, are they equivalent?
They are totally equivalent, because I told you that it's this thing which matters, and this you can achieve either by, this is the formula. So it's about just your mental picture. You want the U to act on psi or act back there. So they're totally equivalent. But you have to pick one of them. Well, actually, you can pick infinite number of pictures. You can divide some part of evolution, divide this U into two parts. Let one act here and let one act there. So then you can have that a little changes are in the state and a little changes are in the operators. Or you can keep all the changes in. Is this still working?
Yes.
क्योंकि मेरा कंप्यूटर की बैटरी नहीं थी, वो खत्म हो गया. It's still working.
Yes, it is.
Okay, good. तो Heisenberg picture में ये है कि आपने state की evolution totally freeze कर दी है और इस केस में आपने operators की freeze कर दी है. There's a very nice picture you can make. Think of this whole Hilbert space, just for imagination, made up of this is a basis, eigenbasis. So this is one eigenvector, this is another eigenvector, Now, here's your state vector. Now, the probabilities, they depend on these projections. Now, as time goes on, the state vector rotates. And because of this rotation, the probabilities change because projections change. But the same thing, instead of you saying that the state vector rotates, you can say the frame rotates. So keep this here and let the frame rotate in the opposite direction. So that would be the Heisenberg picture, where operators are changing, and as a result, their eigenvectors are rotating. But you can do both as well. This rotates a little and this rotates a little. Why is the rotation? Because it's essentially it's the unitary evolution. Unitary evolution keeps the scalar products invariant. So in the complex context, this is generalization of orthogonal transformations. So this was all about quantum mechanics, and let's quickly see how does classical, how do systems are treated in classical physics. Classical systems. The easiest way to think about them is that it consists of a bunch of particles, and the goal is to describe over here their trajectories in the actual space. There's no Hilbert space or anything like that. The particles are moving in actual over three-dimensional space, and you want to predict their trajectories. So in a coordinate system, the dynamics is described by second order. System. The dynamics. This is our goal, to predict the trajectories described by second order ordinary coupled differential equations. Some trajectories, like if you have a solid object, you can think of it as composed of small particles. So it's their trajectories, but not always. Like, for example, I can consider some kind of a field which exists everywhere. So it's like how that field is changing. That will all be considered a classical system. Well, I should exclude the fields for now because I said I have some coupled second order differential equations. In case of fields, you have partial differential equations. Here you just have ordinary differential equations.
So why second order differential equation is so occurring in nature?
I think the answer is that once you go up in order, the solutions become very chaotic. The world would have been very unstable if it was really governed by third order. So the main content of Newton's laws is just that the equations should be second order. Otherwise, it's just a tautology. It just says that acceleration is proportional to force. What's force? It's just acceleration times mass. So it's just a definition, nothing more than that, except this statement that don't go beyond second order. So this is, if you consider these coordinates. So in a coordinate system, you will have coordinates of the particles, which I'm labeling with I. So I will stand for different components x, y, z, as well as different particles. So if you have n particles, you will have 3n coordinates in 3 dimensions. So things like that. And Newton's laws are just these. You have these. This I'm going to write without any label. So when I write this x dash inside arguments, this means n-dimensional vector. So it has list of all the coordinates and all the velocities. It's just one dot. And dot is the time derivative. There's an m here, but since m will have to be adjusted for different particle types, so I'm just absorbing it somewhere there. Maybe I should write it and write it somehow like this, but then I have to remember कि 3 जो coordinates हैं उनके साथ एक m है, बाकी में solution. So some abuse of notation. So now the main content is guess the forces. Guess the forces so that the dynamics matches with actual system. There is a restricted class of forces. If we consider Cartesian coordinates and which are also inertial, I'm not going to go into detail what's inertial. Then, and the force is of type conservative. This is just a name for this condition which I'm going to write. Then this equation is written this way. No, sorry. There are no velocities. So over here, I included velocities for a general case, but not anything beyond, because then I will be disturbing the second order form of it. So in this case, it's special. What I have is I construct the forces by taking the gradient of a scalar function. This is called the potential. Many of the naturally occurring forces are of this type, but not all. So once I have this one, either these or that, since I have second order differential equation, so I pick the initial data. Which are these xi and xi dot at a fixed time. We have unique solutions. So it's as simple as that. Finding solution is different, but theorems guarantee that the unique solution will exist. Therefore, the state is described by these pairs. Because if you know this at one time, then you know what will happen for all times. So it has all the information about the system. You don't need anything else. So this is the state data, unlike in case of quantum mechanics where it was an infinite dimensional vector. And all the observables would be are just functions of xi and xi dot. So let me take quickly an example. I take this force. So I'm only considering motion in one dimension, and it's this system. It's a spring. This is frictionless. So maybe very smooth, and this is attached to a spring. This is the equilibrium position, I'm calling it 0. If I stretch it, the spring is going to pull it back. And if I compress it, spring pushes it back. So I'm modeling it to this force. This is modeling. And if a spring strictly follows this, I just call it is the half-hour ideal spring. It's because I took this as a model. So this minus sign just means if this is plus in one dimension, you just need plus or minus to indicate the direction. That's it. So if you pull it this way, force is this way. If x is negative, force is this way. And you can also check. This will give you. This is of this type. And in this case, if I write the Newton's law, it's this. So I write it this way because k and m are larger than 0. So I can write it as a positive number. This has general solution. There's a general solution, completely general. You can write it in other ways like a cos plus b sine, or like this, or a sine or something. There's two given initial data, x at t naught and x dot at t naught, a and phi are fixed. And what is it describing? It's just describing harmonic motion. If I pull it, it just oscillates with a sine wave or cosine wave. So this is t, this is x. It just does this. This was just one example, but then you want to make things a bit different, and you redefine the whole thing in terms of something that is called the Lagrangian mechanics. So what's Lagrangian mechanics? For now, I start with force of this type. Then I construct this. Or define this. A function of x and x dot by this expression. Now, when I write this, is just some practice in writing these expressions. I have a square, that means xi times xi. And when I have an index repeated, I mean that there's a sum. So this is truly this. which is just the dot product of two velocity vector of the same velocity vector with itself. Write it back in my favorite notation. Remember, this is just v dot v. V in the n dimensions, collecting all the components. So what do I do with this Lagrangian? I consider paths. So I say that I start with at some time t naught from x of t naught, and I go to another time. Let's call it ti. Go to tf. Some other, let's call this position as x, what am I calling, x naught, and call this x naught tilde. So I say this particle is going to start at position x naught at time ti, and it's going to end up at position x naught tilde at time tf, taking some arbitrary trajectory. So with this trajectory, there is a trajectory x of t, which is this. I construct a functional which takes these paths and gives out numbers. How do I construct it? I just compute the Lagrangian at each point along this trajectory and sum it up, integrate with time. So it's going to give me numbers. But what I do, I keep this fixed. Well, this is already fixed. This is for one particular path. But to remind myself, I put these things. The path starts there and ends up there. Then I say, okay, this was one path. I'm going to consider all kinds of paths. So this particle goes crazy, it follows all kinds of paths between these two, but always starts up here, ends up there at these times. Then I say, okay, I'm going to look for the path which is a stationary path for this function. So when I move around that, when I disturb that path, the action either is a saddle point, is an extremum of it. It either decreases or increases, either a maximum or a minimum. So look for a path which is a critical path for this S. This is called action. So how would you do it? Well, you know that the first derivative, the variation to first order, they have to vanish. You can just, I'm not gonna go over a lot of calculus, but this is just obvious. But so you're disturbing, you're gonna look at a path. For example, this is the extremal path. So you try to disturb and see what happens, but you keep the endpoints fixed. So when you are computing these chains to first order, this is just because it depends, the Lagrangian depends on x and x dot. So I get this and I get this thing, and remember, there's a sum. So I'm summing over all possible i's. Whenever there's a double index, it's sum. I'm just leaving out the sum. So I get this, I can write like this. It's a derivative, so I bring it out. This is quite believable. All I'm doing is when I disturb this path a little, what's the change in velocity? I just compute how I change the disturbance. Its derivative will still give me the change in velocity, because the derivative of the original path gave me the velocity. I change it a little because it's first order, so this works out. Now what I do, I want to make this variation independent of this. So I integrate by part. So what happens is the integration comes to this side. The differentiation comes to this side. And this becomes independent. And I have a surface term. At the endpoints. Here. So since I'm not doing any variation at the endpoints, they had fixed, this goes to 0. So now I have this. Now for this to be 0, for this to be action to be stationary, this has to be 0. For arbitrary variations, it will be 0 if this thing is 0. So this, any path along which the Lagrangian satisfies this, will be the stationary path. These are called the Euler-Lagrange equation. It must have worked sometime over this.
एक फेमस वो है कि ना लैग्रांज ने अब वो काम किया जो हॉयलर ने किया।
क्या वो स्टूडेंट टीचर का रिलेशन तो नहीं था?
नहीं पता नहीं क्या था सर वो, लेकिन लैग्रांज ने पूरा मोशन की तरह माना है।
Maybe he just wanted to let's just repeat what Euler is doing and put out my name on it. So this is a completely separate logic from Newton's equation, but what the end result is still the same. It's just a new way to do that. Because if you check,
दोनों से जो मैकेनिक्स मिलेगी वो इक्विवेलेंट होगी, मतलब एक तरफ फोर्सेस को हम सम करते हैं F is equal to m और एक तरफ ऐसा लगता है जैसे हम लीस्ट मतलब एक्शन को मिनिमाइज कर रहे हैं, दोनों से सेम डिस्क्रिप्शन.
I'm going to make a comment here. One is probably more general, or at least easier. So this is more easier. So these are just Newton's equations in this case, because to start with, I said I'm going to construct my Lagrangian like this. So अब आप ये देखें, dl by dx dot I dot. What is this? This is just mxr dot. What is dl by dxi? This is just minus dv by dxi. So Euler-Lagrange equation tell me mxi dot d by dt is minus dv by dxi, which is the Newton equation. So if I construct the Lagrangian this way, I'll get the Newton's equation back. But there are these two important points. First one is that it's a scalar function. So if I change the coordinates, I should think of it this way. The particle has some trajectory. And if I change the coordinate, where the particle is and what its velocity is, that I can give it different labels, different numbers, but it's still in a geometric way it exists. And this Lagrangian is taking that input. So from xx dot space, it maps it to some number. So if you think of it as a configuration of x and x dots, then Lagrangian is a scalar function on that. So if I change the coordinates, it will change to something else, but the number will be the same, but functional dependence will be different. However, since it's a scalar, so this change of variables would be easier compared to if I start with the Newton's equation. There, if I have to bring out a change of coordinates, it is a vector equation, so it will require a lot of care. Here, it would be easier. But on top of this, if I change the coordinates, I take this and I look at this thing. The path doesn't care which coordinate you are writing it, it's the actual path. So I plug it in here, this changes into, this form is different than that, but it's the Lagrangian of the same system in new coordinates. Now look at this. In all this calculation, starting from here, I'll be just replacing xi with qi. No change at all. So in any coordinate system, this form would be valid. No matter what coordinate system you take, this general form of the Lagrange equation would be same. While this is not true for Newton's equation, at least the way I wrote it, you change it, coordinate system, it drastically changes. But more importantly, what if the force was not of this type? So I showed the equivalence using this. So the force is of this type. What if the force is not of this type? What if the force has velocities in it or whatnot? Well, you say that we still look for a Lagrangian whose variation is going to give me the correct equations through this process. So then the point is that you are guessing a function whose variation through action gives you the correct dynamics. Then who says that Newton's game of guessing is superior to this? In Newton's case, if you see a system, what you need to do, you need to guess a force which reproduces it. Here I'm saying, okay, stop doing it, guess a Lagrangian. It may have no relation to how you go from Newton to here, you just start from here. Take it to be the starting point. No harm in doing that. And actually it's superior because in Newton's case, you have to guess a lot of vectors for each particle. Here you're just guessing one function. And not only that, actually it turns out that when you go to more complicated things like field theories and subatomic things and whatnot, not only subatomic, like extragalactic things like general relativity and whatnot, this is a much superior method to guess because you can guess based on symmetries. While in Newton's case, it's very hard to argue what are all the symmetries and how you should build up the forces. So we say that guessing the Lagrangian is an independent starting point. And therefore, the function is considered this Lagrangian in its own right. Forget about guessing the forces, just guess the Lagrangian. I want to do one example to stress this point, that changing coordinates is much easier. So consider a potential, a general potential, V x y in 2 dimensions. And I want to write the Newton's equations in polar coordinates. Then the Lagrangian prescription is, there is a prescription if you want to guess the Lagrangian based on some Newton's forces, which is just take the kinetic energy minus the potential energy. But you don't have to stick to it. There are general cases where there's no obvious candidate for potential energy, so you have to do something else. So just guess. But in this case, if you want to match, you have this Lagrangian. This is the velocity, kinetic energy, minus this potential, which appears in Newton's equations. And you want to do the Lagrange equations. But I want to do it in polar coordinates. So just change the coordinates. And change it, because it's a scalar, change the coordinate is really easy. And if you do that, this is what you get. But the Lagrange equation, in this case, same. You don't have to do anything different. So you have two coordinates r and theta. You do d by dt dl by dr dot is dl by dr. So this gives you dl by dr dot from here is what? M r dot. And what is this? Now this not only has this component, it has a component coming from here. So you're writing Newton's equation, you have these extra terms. Doing it in Newton would be hard. These are like Coriolis forces and centrifugal forces and whatnot. When I write the second equation, d by dt dl by d theta dot, which is from here, and this I can open up. So although it's a conservative force, but in polar coordinates, it has velocity dependent terms. So conservative, that form only existed in Cartesian. This is exactly what Newton would give you, but in Lagrangian form, it's much easier to get. And not only that, in Newton's equation, you would be, suppose if I say that this is of this form, a function of the length. So a function of r only, no phi. In Newton's case, it would be hard to guess what are the consequences of this. But in this case, if a coordinate is not present in the Lagrangian, like if then this equation will give you well, actually you should look over here. This will always vanish if a coordinate is not there. So this quantity will be conserved if Qi is absent in L. So we discover that this combination doesn't change, which is a very hard thing to guess. This is, by the way, called the angular momentum. As far as I can tell, I think Newton never knew about angular momentum, so he should define something like that. And this is just in 2 dimension. In 3 dimension, it becomes extremely useful, angular momentum, because it kind of gives you 3 integrals of the motion, 3 components which are not changing with time. So this is like a quick tutorial on Lagrangian mechanics, and there's further escalation of it. Well, not escalation. Well, yeah, I think it's more general than this. So like this Lagrangian mechanics seems to be more general than Newtonian. And in one sense, it really is. Because if you want to do quantum mechanics, there's no way to Newton's laws, but through Lagrangian mechanics there is. There's another, let me rub this and use this board. Mechanics is called the Hamiltonian. Developed by Hamilton. So what you do this time, again, I'll start with the easiest example when the force is conservative. So you construct this object this time, very close to that, but this time you put a positive sign. Now you define we call it momentum. Then you want to replace this over here. Then this h becomes a function of x and t, and you get this. So it's sort of like kinetic energy plus, not sort of, exactly kinetic energy plus potential energy. Then we can write down. Now the genius is that you have to change your perspective. You have to think x and t as independent variables. So then we can write down the following equation. So what are the equations? Well, from Newton's law, dpi over dt, which is pi dot, this is just m x double dot. So this should be equal to minus dv over dxi. But looking at over here, I can call it minus dh over dxi. So I like this equation. Pi dot is this. And from the definition, this definition, xi dot so pi over m, if you look over here, is this. This is for now, this is just the definition. But changing the perspective, I'm thinking of it. Now I think of xi and pi to be my basic variables, independent variables. And then I say that these are the equations which govern them. And these are, and you forget all the previous steps. Focus over here. Then these are first order ordinary differential equations. So you have reduced your problem from second order to first order. The price you have paid is you have doubled the number of equations. But that's fine. It's at least first order. And you can find the solutions if you give this initial data. If you give the positions and momenta at time t0. So these are called then the state variables or phase space points. Phase space variables or points. So now you think of your phase space consisting of position and momenta, and you pick a point here. These Hamiltons, these are called the Hamilton's equations. They're going to generate what happens later on. But this was for the special case when the forces were of this type. What if I have a very general dynamics? Well, I know that for a very general dynamics, I can just guess a Lagrangian. And Lagrangian also works in any coordinate system. And it has lots of symmetry, which I can consider. So is there a path to this from Lagrangian? Well, there is. This is through the Legendre transformations. You can do these transformations to a lot of things, but I'm just gonna do it specifically to Lagrangian. So a root to Hamilton's equation to Lagrangian. So consider a general Lagrangian like this, and it's not Cartesian coordinate or anything like that, any general coordinates. And define Pi as dl over dqi dot. Like here, Pi, I said it's minus dh over dxi. You can check that in the conservative case, it becomes dl over dqi dot. But now you say, okay, conservative or not, whatever function I have guessed, I cannot even split it into kinetic and potential or whatnot. Whatever function I have got, I'm going to define the Pi through this partial derivative. And then this Pi would be a function of Qi and Qi dot, because that's what the Lagrangian is a function of. Assume it's assume it is invertible, which in most cases it is, because it's just a quadratic form. Usually you don't want to have too complicated of a thing, or at least locally it is. So you say that solve for Qi dot, since it's invertible, in terms of Qi and Pi. Then you define this guy. This is the step which we call the Legendre transformation. Again, there's a sum over these. And you think of this thing, as I have written over here, as function of Q and P. Because this guy, I'm really thinking that I have a functional form for it in terms of Q and P. Similarly over here, is some functional form of Q dat in terms of Q and P. So I get a function of Q and P. Then I consider this. Partial derivative. So I get a Qi dot. From here, I get from this, I have another term because this Qi dot depends on Pi. So I have, by Leibniz rule, I have Pj I have to change the dummy index because it's a sum. Then I have dl by dqj dot dqj dot over dpi, because the dependence on pi only enters to q. It's only q which depends on pi. But what is this?
Q या Q dot?
ये कौन सी?
Q dot depends on.
Q dot depends on P. So what is this thing? It's written on the board. नहीं, सिर्फ ये derivative dl over dqj dot.
Pi.
Yeah, so it's pj. So this is pj. Then these two cancel. So I get this equation. Similarly, when I do this, dh by dqi, यहाँ पे तो कोई डिपेंडेंस नहीं है, सिर्फ यहाँ से आ रही है माइनस dl over dqi. Now I use the Euler-Lagrange equation. Euler-Lagrange equation says that this is minus d by dt of dl over dq dot. But dl by dq dot is pi. So it's minus, which I'm going to bring to the other side, is pi dot. So these two are those. So these are Hamilton's equations. So that means if you define, you want to eliminate some variables from here, q dot. This is eliminating them using the Legendre transformation. Define this, then this function becomes this, and the equations are reduced to first order form, and they are this. But you use the Euler-Lagrange equation because this was just definitions, no dynamics went in. So where was the dynamics? The dynamics came through Euler-Lagrange equation. So in fact, you can start with this, put it in the action, and write the action in the form of h by taking this to the other side and bringing it to that side. Write Lagrangian in terms of h minus p. Well, p minus h. And do the stationary thing, you will get these equations. Or you can get directly like this. So these equations, what time is it?
850.
8:50. So I should kind of hurry up. These equations are extremely interesting because these equations are the ones which have given rise to a whole field in geometry, symplectic geometry. What you are seeing over here is essentially symplectic structure entering, which we will discuss probably next time. But today I should just tell you another way to cast these equations. So observables in classical mechanics are just functions of state variables, phase space points. We just construct some functions of these. So suppose you want to find the dynamics of one of this guy, how it changes with time. So it's just going to be, if it doesn't depend explicitly on time, it's just going to be now I use the Hamilton's equations. So I have kind of this thing that I have partial derivatives of A and H. First Qi, Pi, then Pi, Qi. So it's kind of an antisymmetric structure. I give it a name. So this is Poisson bracket. And it's defined for two operators, not operators, two functions of phase space. So this formula, dA, dQi, dB, dPi, and then exchange the order of these guys. You can check that they are antisymmetric. They act as derivatives. Derivatives in the sense that they follow the Leibniz rule. They're linear and satisfy Jacobi. So I hope you know all of this, what it means. I don't need to write. But if you compute so what is here? It says A dot is this. You can check that this Q dot, this is true for all functions. This equation is the same as that. You can just check quickly. Similarly, P dot is Ph. So it's easy thing to remember. They all take the same form. So this is the dynamics, how Q and P or any function changes. It changes to H, which is generator of time translation. Now compare it with what we just derived like half an hour ago for the Heisenberg picture operators. That was something like A dot is. So it's very, very close to that. These looks like that.
ऐसा होता है जैसे वहाँ पे कॉम्पिटिटर आ गए साथ में आउट आ गए.
So that's the rule of quantization. Take the Poisson bracket, replace the bracket with iota times the commutator. So let's check one more thing. These are non-dynamical brackets. So because I can compute it for any two functions, qi, qj is 0. 0. You should really go and check at least these. This is very easy. So they have this structure between them. These are called the canonical.
Sorry, QI PJ नहीं होगा.
Yeah. Canonical Poisson brackets. Why canonical? Well, suppose you change these qi, pi to something else. Mix them up, do whatever, some transformation. But make sure that these new ones have still this and the rest too. You might think that this would be a very restricted class, but actually it's a very, very large class of transformations which preserve this canonical structure. And these transformations are called the canonical transformation. And now what happens is, suppose you want to compute this. So this is going to be this. H QP, but you replace H with these. So you get this, and you get this. This doesn't matter because it's just change of labels inside. You can prove it, you can show it. So it seems like this is computed in the old Q and P. But what if you do this? Take the old Q and P and compute the bracket in the new Q and P. You still get the same structure. So what you have in general, you can easily show it. As long as these hold. So this is the main requirement of canonical transformation. As long as it's canonical, you compute the bracket using the old or the new, there's no difference. So they are all, in a sense, at equal footing. The one you started with had nothing special about it. So you just take any Q and T, any canonical coordinates. So these are called canonical coordinates, canonical phase space coordinates. How they are canonical? Because their brackets are canonical. So you just start with some coordinates and you say, okay, you can just declare it. These are canonical because their brackets within themselves are these. And then the game becomes, you can forget about Lagrangian. You came from any Lagrangian. You say that I have a phase space consisting of coordinates and momenta. And coordinates and momenta have these brackets. And then I have to guess a Hamiltonian. guess a generator so that when I write the Hamilton's equations, these or the most general ones, these, they give me the correct dynamics. So the guessing game has now shifted to finding H so that these gives you the correct equations. So these transformations are actually more general than coordinate transformation. Coordinate transformations are called the contact transformation. These mix coordinates and momenta and all that. And it's a very large class. And there's a lot more which one can do here. For example, one can write all of this in the form of symplectic geometry. Forget about these coordinates as well. Write everything geometrically. You can do that. Okay, let me stop here.
I have a question.